It's very nice to meet you. I'm really sorry that I was not here before. I had an unforeseen commitment, so I was in Greece the last few days, and I just flew back yesterday evening for the lecture this morning. So it was very nice to hear this recap. There's a few things that we heard from Jalal about defining an uncertainty set, about polyhedra, etc. And that's why I thought that would be nice to make this lecture about forecasting, because that's the other side of the story. There's a bunch of people who do optimization, data-driven optimization, etc. And then there's another bunch of people who want to play with data and predict some information for people doing optimization, decision-making. And based on what the optimizers or the decision makers want, we define forecasting products that just fit. So for instance, talking about polyhedra, there's a collaborator of mine, Farhana Golestane. She was the lead author of a paper published recently where we directly predict polyhedra to be used in robust optimization and chance constraints optimization. All right. Another thing is that I thought it would be nice to make the lecture quite introductory and then to build up. So it's going to be very, very nice and easy at the beginning, and then we'll go to more advanced stuff. I've heard you had a good sailing trip yesterday, right? Yeah, so now you all relax, a good sailing trip, a good night of sleep, and now we can have 2 more days of the summer school. All right, so I'm not going to introduce myself. I think, yeah, Jalal may have done it already on Monday morning. If you want to chat, I'll be around today and tomorrow. All right, so what are we going to discuss? It's forecasting. With application to renewable energy, and then eventually you can plan that in some optimization problem. Oh, it's a bit strange, the display. I'll try to fix the display, sorry for that. Yes, now it's back to good. All right, so we'll have 3 parts. The first part is about the basics of forecasting, so that we agree what we're talking about. The second part will discuss learning. I know that Munter on the first day had a bit about learning, but he looked more maybe at a theoretical view of learning, while here we'll go very practical, what we want to learn and how we're going to learn it. And then the third part will be hands-on. So I need to know if you program in R or in Python or in MATLAB. Do you all program? Yeah? Okay. We'll make some groups, but we have a bit of programming to do. It's going to be quite easy programming. You'll have to do a bit of math on paper, and then we'll program everything so that you do some online learning. All right? Okay, so to start with the forecasting, we'll discuss why we care about forecasting for renewable energy. Most of you know, but just to be sure that we're clear. We'll discuss some forecasting products. When I arrived here, I heard 2 gentlemen discussing various types of forecasting products and why we care for decision making. And then we'll have a quite straightforward introduction to verification. And verification will be here just for the deterministic case. I think if we go for the probabilistic stuff, it gets a bit heavy for a Thursday morning. So we'll stick to deterministic only. All right, so basic forecasting concept. How many of you have done some forecasting ever? Wow, okay. So that's a good crowd. Normally, there's not so many people doing some forecasting. When we had the summer school previous years, people were asking for some more forecasting, actually, because they didn't know anything about it. So it's nice to have a few. So if you think it's a bit too introductory, just raise your hand and say faster, faster, please. I was in Thessaloniki in Greece for a conference on forecasting. Every year we have a conference where it's people doing forecasting for everything. So actually this slide is quite, I'd say, fresh in my mind. These last few days I've been discussing forecasting, for instance, for sports. We had a guy, he's a specialist in sports forecasting. There are some people forecasting traffic, demand for goods, for supply chain management, logistics, etc. So if you think of forecasting, it's something that we do everywhere for many, many different types of application. And actually, one thing that's very nice in the power and energy field is that we've been extremely consistent in bringing forecasting to optimization or to decision making. If you had seen some of these talks in Thessaloniki this week, in many fields, they're still at the stage where they do forecast because there's some executive director who want to have forecast, some insight in the future, but they don't really know how to use the forecast, right? It's just some information, they're just curious about it. While in power and energy, I think over the last 10 years, we've been really, really good at making clear we know what to do with our forecast. Right, so that's what I mean here. We want to make decisions. Forecasts are really there to make decisions. But even if it's really good to make decisions, a lot of the users still today, some of you are from industry, some of you work with people in industry. Today in industry, forecasts are not always adopted, especially if we talk about probabilistic stuff. So it's part of your job, guys, when you work with people in industry to make them adopt forecasting and also your crazy optimization stuff. You know, this distributionally robust optimization, before it's used in industry, we're going to need a few years, if not a few decades. So this would be a few application areas of forecasting, and there's many more that are coming up. There was also a nice topic we've been discussing. It's crime forecasting. And you may or may not agree about it, but some cities around the world will have data scientists doing some crime forecasting, and they will optimally allocate police forces in the city depending on where they believe there's going to be crime in the coming days or weeks. All right, but when it comes to energy, what's interesting is that everybody needs forecast. So for your research or working in industry, you may have different roles. You may be doing some trading, you may be doing, I don't know, working for a distribution grid operator, etc. And whatever your job, you will have an interaction with the market. In most countries around the world, we go towards liberalization, or it's already a liberalized electricity market. So the market will call for forecasting, and optimal operation of power system also calls for forecasting. There's also one thing, I say also you and I, is that in the future, we want the final consumer to be much more involved. We've looked at your motivation letters. I've seen quite a few of you are interested in consumer-centric markets, peer-to-peer or community-based. If we are pushing the decision-making problems down to the consumers, the small people like us, then people are going to want also to use forecast and to be actively using the information in forecast, right? So I believe in the future, we will all have a little app and we'll be looking at forecasts on our mobile phone for energy-related data. Okay, and we want to forecast everything, right? It's not just about renewable energy. We'll discuss renewables, but you may want to forecast everything. I think some people have been focusing a lot on electricity prices. Load forecasting for electric power and energy has been a big thing since, I don't know, the 80s. And now today you want to predict more in the markets, you want to predict congestion, and obviously we want to predict wind power generation or solar power generation. Also wave energy, if some of you are interested, for instance. All right, there's a lot of problems, and I'm not going to go through them because you've been discussing that, I think, already the last 3 days, and you'll be working on that in your research and in your work. But there are many, many problems, and I think today 99% of the problems in power and energy, they will call for forecast eventually, or some kind of description of what the data tells you. So that's what Jalal was saying in the recap. I don't know how Saverio explained it yesterday, but coming from control and optimal control, they have a different view, for instance, of how they want to optimally use the data. And different communities coming to that, they want to better use data, but in their own way. Typically, we have this different form of information. So what Jalal was mentioning with polyhedra, for instance, that would be that eventually you would issue some kind of trajectory, a lot of scenarios, and then you want to define some kind of contour of the space that is spanned by your scenarios, right? Polyhedra is one option. It could be an ellipsoid. It could be something else. You may have some quantiles, some intervals, predictive distribution. We'll go through that afterwards. If you like theoretical works that are around, there's quite a few theoretical works that will show systematically for many decision problems that you can only make optimal decisions if you have the full information on uncertainty. So that's why many of us have invested a lot in all this probabilistic stuff, because we know that if you're not going probabilistic, you will never be able to make optimal decisions. And especially if you care about risk management also, obviously if you don't know anything about uncertainty, you cannot do any risk management. Okay? You can stop me anytime, and the slides are online, you know, if you want to have them. Okay, but so now let's get to how we make the forecast. In this community, there's been a close linkage to weather and weather forecasting community. Today, it's really clear that we're going to use weather forecast, meteorological forecast as input, and we combine that with data locally on site, if you look at a wind farm or a solar power plant, and maybe data in the neighborhood. If you consider the lead time and what would be your forecaster, like just conceptually, you know, we don't talk about metrics so far, and the contribution to forecast error, you will see that the meteorological forecast actually, they are the most important variable for most of the lead times. Only if you predict very short term, you will need to rely a lot on your local measurements. But as you want to predict more than, let's say, 6 hours ahead and up to 2 weeks ahead, it's really the weather forecast that contribute the most to the quality of your forecast. And so obviously if you look at the error, most of the error is in the weather forecast and then it's diffused to your power forecast. There's I talk here about possibly extra info for those who are interested in data science and quite advanced data science. There's a lot of funny things that are being used today that starts to be used. So radar images, for instance, for offshore wind farm. There are some people who use sky imagers for solar power plants. So a sky imager, it can be as stupid as having your mobile phone thrown on the floor with the camera upward, and you just look at the clouds passing, and you try to use that as input to forecasting. So there are lots of funky stuff that's being done today, but that means a lot of data and very complex data science, actually. All right, if some of you know about meteorology? No? 1, 2? Yeah, you can ask something.
Question to the last slide.
Yeah.
Why is the contribution of the measurements increasing at the end of the data?
But so it's more of a relative effect. If you try to predict more than 2 weeks ahead, even the very nice weather forecasting model, they get crap, right? And so actually, then at the end, it gets better to just make long-term statistics. And the long-term statistics are made based on local measurements. So that's why it starts taking over again. And if you want to predict 6 months ahead, then again, you only use the local measurements because there's no weather forecast that's going to tell you anything 6 months ahead. They are trying, I can tell you. Some people are trying very hard to predict the wind 6 months ahead, but that's a bit tricky. Sorry? Oh, sorry, yeah, it's true. I forgot I need to throw this thing around. Okay. Or you throw it. Guys, I don't want to look stupid hurting someone by throwing it, so thank you very much. You're the first one to throw it. Thank you very much. Thanks, Jalal, for... Okay, so weather forecast. I've been working for Weather Forecasting Institute for 1 year. It's extremely impressive what they do. Normally, the best and the most advanced centers, they have a model that is all over the globe, and they have a grid, and they have a model for the fluid dynamics model, if you want, for the equation of motion of the most important state variable. So that's temperature, pressure, etc. And then they predict all over these grids. And also you have to see it's there's another layer because it's you also have vertical layers. And they predict for all of that at once. So if you have like the biggest computer in the world, it still takes hours of computation to issue a weather forecast for all over the globe. The problem with this is that, well, first of all, you can imagine it's a very complex problem. Then you need a lot of measurements to know what's the actual state of the atmosphere all over the globe. Then even though we're very good at physics, we don't have perfect models. So at the end of the day, there's so many uncertainties that add up that the weather forecasts are not perfect. I think we've all noticed that, right? The weather forecasts are not perfect. So we have to account for that now that we say it's so important to have weather forecast as input. We have to account for that when we do our modeling, that they are uncertain. Okay, there's also a lot of aspects that maybe today sound quite obvious for many in the community, but actually it's quite complicated if you think of it. There are some days that if you were, for instance, to look at different forecasts from different providers, or you have different models, the forecast would agree, and then you would tend to think that, okay, it seems to be a quite predictable situation, so I'm just gonna take that, right? Maybe I take an average of these guys, and I'm just fairly certain it's gonna happen. There are some other days that if you were having several forecast providers or several models, they are not gonna agree, and then it's a bit tricky, right? Who are you gonna trust? Maybe you want to pick the best one. You have some kind of reputation-based mechanism to have your favorite forecaster. Maybe you want to take the average. Maybe you want to take a weighted combination. Maybe you don't trust anyone that day. You just say, okay, now the forecasts are crap today. I don't want to trust them. It sounds simple, but there's something that comes from economics. If you look at the economics literature, there's a strand of literature where they look at experts and consensus among experts. This would be a consensus, right? Let's say it's 4 experts that you have here for the 4 forecasts, they agree, and here they don't agree, right? In economic literature, let's say 30, 40 years ago, they also had this idea, if the experts agree, we can trust the experts, right? If they don't agree, tricky situation. But then we've realized there's expert bias. And actually often when the experts agree, they agree on the wrong thing. So we have the same in meteorological forecasting and power forecasting. We have actually noticed that it's not that easy, and you have some days where everybody agree, but they always agree on the wrong thing, right? And there are some days where they don't agree, and actually there's one guy who is right, and the other guys who are wrong. So it's not just averaging everybody and it's going to work, right? So it's a bit tricky when you consider the uncertainty aspects and how you're going to use this information for decision making. Another complexity is the conversion from the weather information to power. Most of you have worked with wind or solar or something else, I don't know. But we have this nonlinear conversion from the weather variables to power. So for a wind farm, a wind turbine is wind speed. For solar power, it's the irradiance. And you will always have this kind of nonlinear power curve. For wind, it's bounded between 0 and the nominal capacity of a turbine or the wind farm. Then you have this annoying cutoff when there's too much wind, right? For solar energy, you also have some nonlinearities, maybe linked to temperature, to the humidity, etc. Right, so we have this nonlinearity on top, and that brings extra problems in forecasting. On top of that, if you were to collect data at a wind farm, you will notice that this is the power curve you get from a manufacturer, and then you have maybe 20 turbines in a wind farm, and when you collect data, you just look at wind speed versus power, and that's how it looks like, right? So it's not such a nice curve, and you're sure about it. These last few days, again, there were many people from Brazil giving talks about wind energy in Brazil, and they were all obsessed with this scatter plot where you have the wind speed and power, and they're like, what do we do with that, right? Because it's a bit weird. We were told it was going to be very nice, even though it's nonlinear and bounded. We have this nice relationship, but in practice, it's very tricky, and you try to model that in the best you can. This nonlinearity and boundedness has an impact on uncertainty. If you were to consider, let's say here it's wind speed and here it's power, and this plot is not from me, it's from a friend called Matthias. If you were to have even Gaussian uncertainty in the wind speed, the Gaussian uncertainty, or any uncertainty you have, here it's just Gaussian, will go through the power curve, and then it would get transformed. So the uncertainty in power production, we look here at a wind farm, but it's going to be the same for a solar power plant or a wave energy farm. It's going to get transformed through the power curve, and it might reshape the uncertainty. So there's going to be some asymmetry in your distribution of errors or your predictive density. It can stay symmetric, maybe here if it's a linear part of the power curve, but then the variance increase, right? Or it could be the same on the other side. It's going to make a probability mass here at the top, and then you have a long tail going down due to this inflection here, all right? So the uncertainty and the shape of densities, when you look at forecast errors or predictive distributions, it's quite complex. So there are people who've been looking at parametrization of these shapes. It's possible, but it's quite tricky to be sure your parametrization is going to work. And some people have been going non-parametric. So that means we try to avoid making any kind of assumption on the shape of these distributions. All right, so now we're going to discuss forecasting products, and I think I should invite you guys who were discussing scenarios and other things to tell you. There's many forecasting products. I would like to say if you become comfortable with forecasting, it's almost like you could invent your forecasting product, and it has happened in the past. There's been a few companies or a few system operators. They've been coming out and actually asking forecasters to define new products. So they just came out and say, for instance, we want ramping products. So you have to predict if there's going to be large changes in wind power production in a window of 3 hours. That's what I want to know. I don't care about what's really going to happen. I just want to know about ramps. I don't know from which country you're from, but there are many countries where they are so annoyed with the fact wind power is just going to be all over the place and be ramping up and down all the time. So you can define your own product, and then we can do forecasting of that. Right, but if we were to be a bit serious, we're going to start from the beginning and see some of the most common products and what they are useful for. First of all, forecast is for the future. We agree, right? There's many people, they just fit models, you know, they look at how good their model is at explaining the past. And that's a classical thing with economists, for instance, you know. After you have the crisis, they fit a model and they say, see, I could have explained it, you know. I'm good. When we work with energy, people are very clear about that. We are not trying to re-explain what happened in the past. It's really genuine forecasting. So that means at time t, I have data from the past. I have some knowledge. It can be physics. It can be what's happening with the wind farm, for instance. Is there icing on the blade, whatever. You have some knowledge up to time t, and we project ourselves in the future, and we're going to try to tell what's going to happen at t plus 1, t plus 2, etc., etc. Okay? We have some notation for that. So t plus k given t, we use this notation. K is the lead time. So you're looking k time step ahead or k hours ahead if you want. Given t, it comes from probability, this notation. It's given. It's like a conditional probability, you know, conditional to what I know at time t. I tell you what's going to happen at time t plus k. And the little hat, it's because we don't really know, so it's an estimate. This notation comes from statistics. When you have an estimate, you put a hat. All right? Good. For illustrating, I'm going to use some data from Denmark. So this would be Western Denmark for you. We're here somewhere, right, on the eastern part that's not represented. And this is a map with the control areas defined by our system operator. Even though we have turbines everywhere, actually they are not properly wind farms. They are turbines that are spread, and they collect them at a transformation station. So this would be all these little dots here. And then there are 15 control areas. We've grouped them even more, so there's 1 to 5. And the overall capacity for this period is 2.5 gigawatts, so it's starting to be a bit older. Okay, so the easiest forecast you can issue and the most used today is this single-valued forecast, these trajectories in the future, and we often call them deterministic forecasts. Do you know why we call them deterministic forecasts? I need an offer explanation. Someone wants to try? Are you too shy? Are you too warm? I'm very warm here. I don't know what they did. They put the heat on or something. Can you try it out? Yes.
I don't know why, but I think it should be called point forecast instead of deterministic forecast. Because deterministic
Yeah, I said they are referred to as. I didn't say it was correct.
Yeah, yeah.
Sure.
Because deterministic forecast feels like it's something, I mean, that it's deterministic. It will be that thing that you forecast.
Yeah.
But they're not, right? So I don't know what.
This was a bit confusing what you said. Sorry, but you need the microphone. Throw at him. Throw at him. And you have a second try.
Okay. I don't know why it's called deterministic forecast, but
I can explain you.
yeah, okay. But I think it should be called point forecast because deterministic forecast gives the impression that you're forecasting something that's deterministic, but you're not.
Yes. Yeah. So this was good. Yes. Oh, can you throw? Oh my God, that's going to be a tricky one.
You're predicting a value.
Yeah.
So it's deterministic. I'm saying the value will be this
Exactly.
at this point.
So that's very good too. Do you want to contribute to? It's going to be difficult to have an extra contribution to these two statements.
I don't know. I think it's
Are
just
you-
stupid. No, I don't know. I guess it's it's just one. It's not one scenario. So
Yeah.
sounds deterministic when you just give
Yes.
us.
Yeah. And the last comment maybe. Good. You're.
Well, I would say because you're trying to predict a parameter, a conditional mean, which is, it's a parameter, so it's deterministic, given the information
No,
that you
because
have.
now that you say conditional mean, it cannot be deterministic. That's what he was saying, right? We
Observe the
said, right?
information, it's
Yeah.
deterministic. Like the past, conditioning.
Yeah, no, I would not really agree. No, we'll get to that. Okay, now you're going to be overshooting everywhere. So stop, it's my turn. Okay, so why is this called deterministic? First of all, forecasting is something where you have a very broad range of different people from different communities, right? And forecasting is not something done just by mathematicians and statisticians. It's done also by people who do physical modeling. Meteorologists, originally, they do physical modeling, you know, fluid mechanics, etc. And these people believe, for instance, the weather is deterministic 50 years ago. Today, they have relaxed that. And so somehow, when they make a prediction, philosophically, they say, this is what's going to happen, right? Give or take. It's not happening, sorry, right? But I was sure Given my equations, given what I know, this is going to happen, right? So because there is such a certainty and it's a one-off thing, we call it deterministic. You have a belief this is what's going to happen. But then when we reinterpret it as mathematician or statistician, we know it's a conditional mean, right? It's given, that's what I write here, given the information that I have, given the model that I build up, given the parameters that I estimated, actually this forecast, this single trajectory, is the conditional expectation. It's the average of what could happen given all this information, okay? So now that I say it's the average of what could happen, does that sound so cool? I mean, does that sound like a deterministic, like I know what's going to happen? Not really. Yeah. I mean, if my contract with you is I tell you the average of what's going to happen, that's not very informative. But still, that's why we define these kind of scores, like RMSE and other things we'll discuss after. Even though it's the average, we try to make sure that what really happens is as close as possible from this conditional average we're informing about. All right, but so these forecasts are very good. People love this kind of forecast, but it's true in practice they are not super informative. So that's why many of us, or this is an example for different zones in Denmark. Okay, so many of us have come up with another idea. So that was the early 2005, right? So people decided to go for probabilistic forecasting. And then you have a completely different view of what the problem is about. You say, I really accept that we have a random variable. So power generation for different lead times, for different locations are random variables. And now I want to characterize these random variables. The easiest piece of a summary statistic, if you want to characterize random variables, it's quantiles. They're very handy because if you can just characterize all the quantiles, you would get the cumulative distribution function and you know everything. Why, if you have only one dimension, right? So, for instance, let's say you consider the median, so 50% chance somehow. This would be here, you have a quantile forecast in bold, right? And it's quite close to the point forecast we had before. And you have to see if a distribution is symmetric, the median is equal to the mean, okay? So, and when distributions are symmetric, then the median and the mean differ. So here you see most of the time actually it seems that my predictive densities, what I believe is the description of the random variable, is symmetric because the mean is equal to the median and here it deviates. So that means there's something fishy that's going to be going on, right? How do you interpret this median, the quantile with a 0.5 level? You have the microphone now. It's your turn.
To speak or to throw it somewhere?
You decide. No one wants the microphone, so I think it's your turn to speak again. So how do you interpret it?
Like in 50% of the realizations, it will be above or below that value.
Yeah. Does that sound better than the previous one? We said before it was the conditional average, and I said it's crap. I didn't say it's crap. I said it's not very good, right? And now I say it's 50% above, 50% below. That sounds super informative, right? It's 50-50, guys. So it's not very good. Okay, I don't like it. But there's an extension that's really cool, and I think one of you was mentioning, you were mentioning that, right? And that's very cool, because if you take two quantiles, that makes an interval. And if you have a quantile, for instance, it's a quantile with level 0.1, you say there's a 10% chance that it's going to be below. You have another quantile, it's 0.9, so there's 90% chance below, 10% chance above. Eventually, oh, here it's a 90%, sorry, so it's 5% below, 5% above. Eventually, I give you an interval, and I promise you what's going to happen with 90% chance is going to be within this band. I find it very informative. Now that's really cool, right? And so there are people who have been pushing for these ideas, and you see you need some cool visualization also. Unfortunately, we have to go through that. When you issue forecast, there's a lot about communication of the forecast. So here it's nice because it's very visual. You had the normal trajectory I gave you before, and now I give you this envelope on top with a promise, 90% chance that's going to be within. And that's where we link nicely to Saverio, who is gone. Thank you very much, Saverio. Or to Jalal. Jalal talked about change constraints, right? Change constraints are all about some kind of promise in terms of probability, okay? So we can provide information on that. for some input information. Good. So now if we push it, if you take a lot of these quantiles, we can actually describe fully the densities. And you have, like here, if you take a slice, I have a lot of quantiles, I have a full description of the CDF. And now it's also even more informative. The problem when you go there is that, again, communication and understanding. I've been interacting quite a lot with industry. If I show them a single interval for a chosen confidence level, call it, they understand, they like it. If you start showing 9 intervals at one with different confidence levels, they call them confidence level, it's not strictly correct. You should call it coverage, nominal coverage rate. So when you start showing them that, then you go into the world of probability and statistic, and it starts sounding complicated. So even though most of you guys, I'm sure, you would prefer this kind of information, our friends in industry may not, right? So please be inventive in the way you just massage the information and give it to them. So finally, so that's your turn to talk, right? This is not enough. This information here, these densities, they are marginal densities. So I'm going to describe what's going on for each and every lead time individually in terms of uncertainty. But I never informed you in terms of the dependent structure among lead times, right? So let me give you an illustration. These are the same probabilistic forecast in terms of this kind of marginal densities, but I've been sampling with different dependent structure. Here it's a white noise, so it's just completely random from k to k plus 1, the lead time. It's all over the place, but you respect the probabilities in terms of envelopes. And here I've put some kind of structure, some kind of temporal dependence, right? For you, maybe you don't see visually the difference. If you plug that in a storage model, the way you're going to charge and discharge your storage to compensate for forecast errors is completely different, right? So there's many decision-making problems where you have temporal dependencies, spatial dependencies. You have a network, network constraint optimization problem. You will need this dependent structure, okay? So many of us have been proposing methods for how you model these structures. We'll have a lecture about copulas a bit later today, right? And it's very difficult after to verify these trajectories. It can be easy to use them in optimization problem. I don't know if Jalal and others have been discussing that, but we've all done scenario-based optimization. These are your scenarios. If I issue these scenarios for many wind farms that you put on a network, you can plug that directly into scenario-based optimization. Maybe you need to do some scenario reduction first, but we know how to do it. There are some packages, So by doing that, by generating this kind of product, we're actually nicely interfacing with the optimization community because we give them the scenarios that they want, all right? Good. So these are example scenarios. Here for Denmark, for instance, I told you there are 5 zones. So when I issue scenarios here, I have both the temporal dependency and the spatial dependency. It gets a bit complicated to model that, but I think after a few months of work, you just manage. Okay, so quickly at the end, I want to discuss verification. And we're going to go very fast because today we're not going to go into verifying forecasts. But it's just, I think it's a nice basis for you to understand the philosophy. Good, so I have a test case that I use a lot. It's a wind farm here in the northwest of Denmark, Klim. It's the power curve I showed you also before. We have data for quite long periods. The wind farm has been decommissioned and recommissioned, so actually it's not like that anymore. And yeah, we've produced a lot of data, of forecasts for this wind farm that we use for courses and other things. All right, I told you about this aspect that forecasts have to be genuine. It's the same when you do modeling. Whenever you have some kind of data science project, you should always be systematic and keep a part of the data for modeling. You do anything you want with it, right? And a part of the data for genuine evaluation, okay? And it's for preventing what we said earlier, like the economists would tend to do. If you use all the data and you fit models, you're just going to explain what happened in the past, right? So you should somehow recreate or mimic the fact that you have information up to a certain point. You fit your model, you freeze everything, and then you do as if it was really the future, new data come, and you try your models on your new data, and you see how you really do, okay? So that's why many of us have been setting up forecast competitions for courses or for researchers out there, because when we design forecast competition, we ensure somehow that people cannot cheat, and they really have to split the data in a proper way when they are evaluated. Okay? Good. So the first approach to verifying forecast is visually, right? Have you played with forecast a lot? We have our forecasters in the room. I have. No, the forecasters in the room have not played a lot with forecast. I hope so. How many plots do you make of your own forecast or the forecast you use? A lot of plots, right? So you should go sit with meteorologists. Meteorologists have an obsession. You know, every day they make maps of what they're forecasting or this kind of temporal trajectory plot, and then systematically they look at them. And I think it's very healthy. You want to see what you're actually saying and how it compares with reality. While most of the data scientists you will meet out there, they will not do that. First, maybe they have so much data that they say, okay, it's going to be crazy to have to make all these plots. But also it's cultural. I think a lot of the young people, you know, these young data scientists, they don't really care as much as the old generation. The old generation, meteorologists and others, when they make forecasts, you know, they really want to understand what's going on. And they could even go like, you know, zoom on a little something, and why do I say it's going to pick up and actually there was a drop, you know? Actually, it goes the other way. They can become obsessive about stuff that don't really deserve much attention. Okay, but still visually, when you do that, what you can see is that there are some periods where you can do not so good, right? And there are periods where you can do amazing, okay? There's also some stuff that you can see. There's some very specific characteristics of the forecast that your forecast users will care about. Most of your forecast users are not experts in optimization. They are not experts in forecasting also, but they have some basic intuition. So they will want to discuss with you. It's almost like a communication problem. They're going to want to discuss with you and have a common understanding of what makes a forecast good and a forecast not good, right? So here, how would you characterize this forecast, for instance? What would you say? Nothing? You say nothing? Not good. Not good. Okay, more than not good. What do I miss here?
All the variations.
So I miss the variations. It's not variable enough in a way, right? What's wrong also? Yeah, the magnitude. I'm just off, right? I predict I'm half of the level of what happened, okay? And then this one. So it's good, I guess, right? Cool. Thank you. So it's good. But can we say more? Sorry? Vasilis, right? I heard you.
So there is some lead time on the way.
Oh, you don't have the microphone. Guys, you have to throw it. Jalal is going to hate me otherwise. Tell me.
There's some lead time on the observation, what's happening in the forecast.
Some lead time in the observation. You mean some delta?
Some time displacement.
Okay.
But the magnitude is fine most of the times.
Okay. You're a tough client, huh? Because making a forecast like that, I do like him. Sorry, I don't know your name. But I just say it's good and I stop there.
It's a good forecast, man.
I didn't want you to criticize. Actually, I wanted you to tell why is it good. And you find some negative stuff, you know. No, it's not perfect. I mean, see that. See this one. Sorry, but
So it follows the magnitude and the
yeah,
trend.
sorry guys, he has a very good point actually. It's just, it was not my question exactly.
Okay,
No, so
sorry.
he has a very good point. What is amazing with this forecast, it's not perfect, but it's amazing, is that it really has the shape in terms of timing and magnitude. Most of the forecasts you're going to see, most of the forecasts you're going to play with, since they come from weather variables, you have to think about what happens with the weather. Often the weather forecasts, if they are wrong, it's not in terms of the shape, it's in terms of the timing. So we know there's a big weather system that's coming above you, you know there's going to be rain, we just predict it too early or too late, right? So you see here, it's exactly that. The wind is going to drop and it's going to pick up again. We have the timing right. And that's really cool, especially when you're in Western Denmark, I can tell you, because the weather system come directly and hit Western Denmark, it's very difficult to have the timing right. Okay, and then at the end, well, okay, you know, 2 days ahead, we can relax a little bit. We cannot do perfect all the time. Good. So this is what we were just discussing. There might be some magnitude errors. There might be some timing errors. There might be many other type of errors that have a meaning to your forecast user. So if you were to do more forecasting and interact with people from industry that are your users, you have to kind of develop this communication mechanics. There are stuff they want to see in the forecast, and that are stuff that are, let's say, intuitive, right? And that relate to the physics of the problem. Okay, but still, since we are a bit mathematical, we need to be a bit more quantitative. We're not just going to make plots and say, oh, it looks good, does it look good, you know? Ask Vasilis' opinion, what could we do better? So we're going to define the forecast error. And now it's, it's very, very, very basic. The forecast error is what was observed minus what I predicted. You cannot do simpler than that. Oh, yeah, you could do the opposite. You could do the forecast minus the measurement, right? But the convention is measurement minus the forecast. It comes from statistics. We normalize this forecast error. So we divide it here, you can see, by the nominal capacity of the wind farm, and that makes the errors are between -1 and 1. We agree? It's not between 0 and 1. It's -1 and 1, because you have to think of the worst cases. Okay, when we've defined these errors, you see for a series of forecasts here, you could calculate measurement minus forecast, and you will see, for instance, something that it's nice to discuss with your forecast user. When you have a timing error, you know, you at first glance, when you make a plot, you just think, okay, there's a delay. But if you think of it in terms of volume of energy that's involved, that's going to be that, right? So you see that there's really a big jump in terms of a volume of energy that needs to be balanced because of this timing error, right? That's this bump here. While for the rest of the time, you see, even though the magnitude here of the error looks quite high, that doesn't look that crazy in terms of balancing. And it's called a double penalty effect, you know. When you have this timing issue, it leads to much bigger errors, actually. Even though visually, at first sight, it doesn't look like it. Okay, then we define scores. And scores, we have very easy scores when it comes to deterministic forecasts. It gets much more advanced when you have more complicated forecasting products, when everything becomes probabilistic. If you go deterministic, that's why I wanted to stick to that. It's very simple. You have a bias. A bias is a systematic error, okay? I just take the average of all my errors, and that gives my bias. So what do you want this bias to be? 0? Is this a necessary and sufficient condition for saying that the forecasts are good? No? Is this sufficient or is this necessary, you think? It's necessary, okay. So yeah, it's something that we want. It's necessary, we want to make no systematic error, but it's not sufficient. If you make no systematic error, you can just be all over the place, but on average, your error is 0, okay? So that's why some people have looked at other metrics, and these other metrics, somehow they look at higher order moments of the distribution of forecast errors. RMSE is actually another way to calculate some kind of standard deviation of this distribution of forecast error, you know, up to a normalizing constant. And then this mean absolute error is an average of the errors in absolute value, okay? These are quite nice metrics. This one, because it's used everywhere in engineering. RMSE, you know, if you've done signal processing or whatever, people use RMSE, so it's really broadly accepted. And mean absolute error is very nice because you can directly relate, I'd say, to the discussion here on what it represents. When you make an average of absolute values, you can say, for instance, on average, you off by 2 megawatts. You can interpret that, right? But an RMSE, since you have the square root and you have the squared errors, it's not like you can directly say on average you're off by something. It cannot be directly interpreted. Okay, we typically plot these guys as a function of the lead time. So you will find again that it's easier to forecast for shorter lead times. You see here that's the error in percent of nominal capacity, since we normalized everything. And the error will grow a bit at the beginning, and then it will grow, let's say, less rapidly, you could say. And this is the bias here. It tends to be close to 0. All right? I want 2 minutes to finish that. We define skill scores. The message with that is that it's very difficult to know if your forecasts are good or not just at face value. If I talk with some of you, I don't know, you issue some forecast and you say, Pierre, my forecasting error is 2 megawatts. Say, is it good? Is it not good? I don't know. Could you do better? I don't know, right? So you have to compare with something else. So if you start telling me my forecast error is 2 megawatts, but his forecast error was 1.5 and her forecast error was 3 point something, then I start having an idea of what was possible or not. So normally we define some benchmark. There's persistence. What you see is what you get. Last measurement is your forecast. There's climatology. So you take the average of everything you get from the past, and that's your forecast. You can have some other benchmark. So you can have, I have a friend who was telling me he organized a forecast competition in his course, and he points at one TA in the course, and the TA is the benchmark, whatever happens, right? And he was saying the story is very funny because some years he has very good TAs, and some years he doesn't have very good TAs, right? So he's had some years where everybody beats the TA, and he has some years where nobody beats the TA, right? So the students can be very happy, or not very happy. So here in terms of benchmarks, normally these two are very easy to beat. So you can only be happy, right? Okay, if you were to compare that, eventually you have some kind of improvement metrics because you want this, I'd say the performance of your own method to be better than the benchmark. So you have this kind of improvement and they're going to be positive, and you want to analyze that as a function of the lead time maybe or some other variables. The last thing I want to say, and then we stop for this first part, is that these are just summary metrics. And again, when you connect with people in industry or people maybe who don't have a background in mathematics or in statistics at all, they are very happy with these summary statistics because they have this one number that seems to tell everything, you know. If you say the bias is 0, the systematic error is 0, people are very happy. They understand, right? But if you start trying to give very complicated information, they get lost. One type of very complicated information, that would be to show the distribution of errors. I'm sure most of you are PhD students, you have very good education, you're smart, you're driven. You see a distribution of forecast errors, you're like, yeah, okay, I understand, you know, I can read that. Many people will not be comfortable with distribution of forecast errors and not know how to extract information from it. So if you were to want to know more about the forecast errors, you have to go further than the metrics. You collect your forecast errors and you're going to make distributions. So the distribution can be, for instance, as a function of the lead time. It can be for different locations. It can be for different things. So here, for instance, what do you see if you compare these two? Do you see something that's striking? Nothing is striking? A bit striking? Yes? Throw the mic. It's gone. There, in the middle, there.
Wait.
Damn, you're good.
The
3
second-
days of training.
The second graph is more heavy-tailed.
Yes?
So
That's good.
you make more frequently bigger errors.
Exactly.
Okay.
All right. So that's one way. No other comments? The complementary of these comments. If you look at this one, the frequency of very small errors is also less, right? So when you predict further ahead, it's not just on average you're doing worse, it's also you make less of the small errors. You make less of the small errors and more of the very high errors, right? And here there's also a side. There seems you make more high errors on one side than on the other, right? And that happens quite a lot. If you look at solar power or wind power, it seems that some of the worst errors are all on the same side, right? And it can be depending on the sites, by the way. You have some sites where you can over-predict by a lot. There are some sites where you under-predict by a lot in the worst cases. So you can start analyzing the shape of this distribution, trying to slice also, try to say, okay, for instance, what are the number of times I make errors that are more than a certain percentage of the nominal capacity, so some kind of quantile information. You can have some kind of interval information. So you can go much more advanced in terms of the information on forecast errors, but then it will be more difficult to communicate that to your users. All right, do you have some questions? Yes, and we have. Throw the mic.
We noticed while there was this quantile forecast for the interval forecast, there was some sort of a saturation that we reached very far ahead in the future.
Saturation?
Yeah, so it doesn't seem like a funnel which keeps on increasing.
Yeah.
Could you explain why is that?
But so, I mean, the uncertainty can change based on so many things. So it's the weather situation, the lead time, it can be different things. So it's actually coincidental here that it seems it saturates in terms of width of the interval. You will have situation, and it's disturbing also for most of the forecast users, where the uncertainty is going to grow, and then it's going to tighten again, right? And it's really true. In terms of weather forecasting, it can happen that it's more difficult to predict 24 hours ahead than 48 hours ahead. Again, what I said, I know a weather front is going to come in 24 hours, but I'm not really sure when it's going to come. But after it's going to pass and it's going to be sunny again, and then I'm sure of that, right? So it can happen that the uncertainty just grows and then tighten again. So here it's just coincidental. It grew and it stays, but it's just, okay, I'll change the example, right? Final question, and we take a break? Yeah, Vasilis?
Can you go to the skill scores, the formula explain a bit because I think I missed something.
Yeah, so the skill score, the way we define it, here it's 1 minus the score of your approach versus the score of the reference. So for instance, if your approach has a score of 0.1 and the reference has a score of 0.2, you have 0.5 as a skill score here, right? Okay? If you're doing the same, if you have the same performance that your reference method, this is going to be 1, so 1 minus 1 is 0. So that's why if you do the same as your reference, it's 0, and then anything you do better, it's an improvement. So that's why I was saying it's an improvement here in percentage. Okay? So in this part now, I discussed the basics. Now we're going to discuss learning. And so it's not going to be like the first day with Monter. Monter and I think we have a lot of interest in common. But when I saw the way he talked about learning to you, I was actually thinking maybe for a first morning I would have done it, I'd say not differently, but I would have gone to simpler starting topics. So you're going to have the simpler approach today instead of Monday. And when it comes to learning, we're going to put ourselves in a regression framework. So you had your basic in statistics. If not, you will see it's not very difficult. One of the things I want to get to is online learning. And really one of my main objectives is that you realize that it's very easy to do these kind of things. You just have to remember your basic linear algebra, have a little skill in implementation in R, Python, MATLAB, and then we can actually do some online learning. So from now till, 30 minutes after lunch, normally you're going to start from 0 in online learning to have actually something working on your laptop. Right? We cross fingers, okay? There's one thing we just rapidly touched over the break. It's cross-validation. I'm not going to discuss it today. I don't think so. I say time allowing. We'll see. I'll look at my clock. If I have time, I will discuss it, but I don't think so. I'll give you a link to YouTube videos where you have a discussion on that. And there are the slides also there, so you can just look at the slides while watching the video. How many of you have done regression once in their life? This is nearly perfect. And for the others, why have you not done regression? What prevented you from doing it? Okay, I have to confess. Also, when I was at school, I really hated statistics, and just the fact I was told regression was something under statistics made that I didn't want to do it, right? But eventually, you realize that okay, data science is big today, and there's some very basic ideas from statistics that is now part of your data science package, and even it's called machine learning instead of statistics now, right? And regression is really the basis of so many things. Because if you manage to design a model, a regression model, eventually we'll just use it directly for forecasting, okay? But when you have a model, you're going to have a set of parameters. And that's where the beauty is that you need to estimate these parameters, and we want to do it in an online environment. And online means that every time I get new data points, I want to update my views on my optimal parameters. There are extensions also you need to consider, because regression normally... you did linear regression, right? Not non-linear regression. Most people don't do... Who has done non-linear regression? Oh, good. Okay, so I see quite a few. And non-linear regression with non-stationary processes. So non-stationary, that means it changes with time. 1. Okay, good. So now there's room for learning a few things, right? Okay, so we're going to consider extension to non-linearity and non-stationarity. And this is in 40 minutes again, so it's going to be a... compact. And if you want to learn more, there are amazing videos on YouTube. There are many good professors around in machine learning, application to energy and other things. So I think if you just Google or pull the string, you will find a lot of cool stuff. All right, so first the regression framework. The way we're going to look at regression, oh, I have some coffee, cool. The way we're going to look at regression is that we're going to put it in context as if it was for a renewable energy application problem, right? So it's something we call a response variable. So that's going to be the power at your wind farm or your solar power plant, for instance. And you have some explanatory variable. It's something you're going to use as input for forecasting. So now as input for our modeling. Here, let's say we have some wind speed that's recorded on site, and we have some power that's recorded on site, okay? We are at time t, and I want to build a model, estimate the parameters at time t, looking at this last, let's say, 120 points here. And then when I fit in my model, the trick is that at time t, I'm going to use my model to predict for time t plus 1 or t plus 2, t plus something, okay? What kind of model can we fit there? When you see this time series, you look at the time series of wind speed, time series of power. What kind of model do you fit? How do we decide on the relationship between these two? Do you have an idea? It's Anna with the microphone. Anna, you're so lucky. How do you decide? No, you don't have anything to say. Okay. Can you pass it to someone else? Who wants to say something? That's Anna. That's going to be a tricky one. So there's a person at the first row who would like. Whoa. It's okay. It's padded. It's padded. It's all right. It's all right. Okay. So it's the last time we try this one. We can throw this way, but not this way. Okay.
Yeah, you can do like a statistical test to see if they're linearly correlated, the two variables you're looking over time, I think.
Okay.
But I don't remember the test.
Yeah.
It's Spearman's Rule.
No, you can be a bit more pragmatic. The pragmatic way is just to make a plot, but differently, right? You can collect all this data one by one, you know, and you see them now not at time series, but as data for couple x, y, you know. So every time t where you have observation, two observation, one of x wind speed, one of y power, you say this is one point in a two-dimensional plane, okay? And now you have 120 points that you put in there, and I mean, you could make a test. Do I have a linear relationship or not? Or you could be pragmatic. You look at the cloud of points, and does that seem to be a good idea to fit a line? Yes, maybe yes, okay? So we're going to say we have a linear regression. And you see, I have this 120 observation, and I'm at a given time t. Why is this cool? Because now if I were to go at time t plus something, and I got new observation, I could still have a window like that. I could still make a scatter plot with all these new data points, still look if it's linear or not, refit a model, and continue like that, right? So a lot of these things could be done with the sliding windows. So you can adapt to new information. So we have a linear relationship, and you say you can all do linear regression, right? So we write a model. That's a linear regression model. We have what we call an intercept. You have this linear coefficient. This was the explanatory variable. This is the response. And we have a noise, right? Do you know what are the properties of this noise that we need to assume? So since we want to make no systematic error, Corey at the point.
It's normally distributed.
Is it really? Right, so this is actually in modern data science, we are not so obsessive with the Gaussian anymore. But no, you're right. Ideally, you want it to be Gaussian, right? Okay. ID? Who said ID? Good. ID, yeah. So that would be nice also. So you don't want your errors to be correlated in time. That's good. But there's two things more. One is that you would like that the mean of this random variable, the noise, is 0. So that means you're not going to make systematic error. And hopefully you're going to capture that with your model, right? If this guy has a mean of non-zero, it means it was the wrong model. You should think of something and change your model, right? But there's another assumption, is that this noise has finite variance. Because if the noise doesn't have finite variance, that means you could make infinite errors, and then you cannot do anything, right? So these are the two base assumptions. And these two base assumptions, they are enough so that you can accept other distribution than Gaussian. There's a lot of work in machine learning where you don't need to care about the distribution. And there's a lot of work in statistics where you can make nicer assumptions about the distribution. It's not just Gaussian. One thing after is that we like to reformulate these models in a compact manner, and so you should get used to that. For me now, I have my parameters in a beta vector, so here it's beta 0, beta 1, and then the explanatory variable is another vector, and here it's 1, because you see the first one is an intercept, so it's like beta 0 times 1, right? And it's always the same, and this one is xi, so that's my, my wind speed input, right? Okay, so now that I have a model, what do I want to do? I want to estimate this guy, right? How do you do it? Visually here? You just double guess? For all our regression people in the room, you're like 90% of the room. How do you estimate beta? There's a package in R? How? Which error? So the square error. You do least square, right? So that's the easiest way to go. And the reason why I introduce it is because you will see it's the easiest way to go online also. It's really, really cool. And I think that's why we like to do least square stuff. It's just so easy to play with quadratic loss functions, right? So we're going to do least square. And normally it's something that we should learn at primary school today. We have this least square estimator that we can have in closed form. So if you want to minimize your sum of squared errors, the errors are this, you remember, it's your measurement minus your model output squared. Sorry, there was a comment? Are you laughing at me? No, okay. That would be bad. All right, so I have the error here. These are squared, and we know, I mean, go on Wikipedia, go anywhere, you will find the closed form solution. So we're going to assemble what we call a design matrix, and that's for all the input that you have for the various times in the past, right? So the last time you have the input 1 xt. Remember my inputs here are 1 and xi, the value at time I. So at time t, that's the end of my window, it's 1 xt. The time before, it's 1 xt minus 1, and so on and so on. And then you have 1 xt minus the end of my window in the past, okay? Then in the vector y, you have all the value of your response variable. So that's the same, you know, over your window here, you stack all the values of this guy, you make a bit vector. So this vector has a size n. This matrix has 2 columns and n row, right? And then we apply this, this formula. It's quite cheap. I mean, you have this matrix, x transpose x is going to be 2 times 2. You invert it, you multiply it by x transpose y, and then you will have the optimal parameter in a least square sense. The optimal parameters in the least square sense means that you have a guarantee that if you use these parameters for fitting your curve through this cloud of points that you have here, you will have the minimum quadratic loss. So in terms of squared deviation between the line and the points, right? If you like these funny things in statistics, actually it's just one way to look at it. There are people, including people in Stanford that are known in machine learning, who said that the best way to fit a line through this cloud of points is to minimize least square. It's something that statisticians invented, you know, it was very handy, but it actually has a lot of assumptions behind. When you do that, that means you actually assume the only error, the only noise you have is this direction, in the y direction, the power direction here. But you could have also some noise here, right? So the quadratic loss maybe is not just in this direction, maybe you would have also a quadratic loss in this direction. And then you may have a covariance, you may have a dependency in your error on both sides, or your measurement error. And then some people have actually defined something that's called principal curves, where you say actually the best line that goes through that is the line that minimizes the distance between the line itself and the points that you would orthogonally project on the line, okay? So this is more like pattern recognition stuff, just so that you know that we do linear regression in a least square sense with the parameter estimation. Yes?
I didn't follow this sentence. You have to explain one more time.
The last part?
Yeah.
So here, when I fit my line, it's like I take a point, I consider the distance in terms of the y-axis, right? Because it's my point minus my model output, and I want to minimize this distance squared, okay? But I say another view, which is from principal curve, is to say, yeah, but actually, if I want the line that best describes the cloud of points, the distance I want to minimize is between the point and its orthogonal projection on the line. And if you think of it mathematically, it has a lot of very nice property to do that. It will truly be the tightest line that goes through a cloud of points. So you can read, it's called principal curves. You can read on that. Hastier and Cipciani, who are the famous statistics professors in Stanford, for instance, they wrote on that. Okay. Right, so you know how to do least squares. Where are we? We are there. Okay. So if I do least squares, you see here I get my two coefficients. Beta 0 is equal to minus 3.9. Beta 1 is equal to 9.2. I have that. And now, as I was telling you, if I'm at time t, I fit this model. What I could do is that I say, OK, I get my next wind speed value. I pass my next wind speed value through my model. I get the power value, right? So it's very easy. I can predict now. Do you see a problem with that? So that's what I was just telling you. Do you see a problem with that? Yes? Yeah, you don't have the microphone. Corey, can you throw in the middle? Yes?
If x is 0, I'm predicting a negative value. I mean, this.
So that's good. That's for the next part. We're going to do nonlinear after. Well, yeah, when you do linear regression, you're screwed. You have to accept it has to be in R.
Oh.
No, we have another problem.
Okay.
I say we are at time t. We want to predict for time t plus 1. I say if you have the wind speed value at time t plus 1, then you predict the power at time t plus 1.
Okay.
Do you have this value of wind speed at time t plus 1? I know you don't have it.
Oh.
I mean, you can get a forecast, right?
Oh.
Okay. So the point I want to make here, and that's, we're not going to do it now, but if you do forecasting in this regression framework like that, that means it's not the wind speed measurements you would have as input here, but the wind speed forecast. Because remember, it's the information that you have at time t. And the only information you could have about the future at time t is a forecast already, right? A meteorological forecast. So if you were to use this kind of idea, you have to use meteorological forecast as input. It's so warm here. I don't know how you survived for 3 days. Was it 3 days like that, so warm? Yeah, kind of. Well, you were in Roskilde yesterday, so it was a bit cooler. Yes? Can you throw
Does this take like the last data points, does it emphasize? So if you want to predict in the future, like that the last bit is kind of more important than...
Yeah. So we can do that. We can do some kind of weighting. We're going to get to weighted least square afterwards. And then another story, which we'll do in the hands-on, is that you can use some kind of autoregressive model. So instead of saying that here the input variable is wind speed, for instance, you could say what I'm going to use to predict at time I, it's my last observation at time I minus 1, right? So then you can condition what's happening in the next time on what just happened, okay? But I was showing you in the first part of the lecture, if you want to predict very short term, it makes sense to condition of the recent information. But when you want to predict further, you need weather forecast, and then you use this regression framework, okay? So we will do a bit of both afterwards. All right. So there is this issue, but another issue, it's nonlinearity. I spent a few minutes in the first part to tell you everything is nonlinear, right? It's bounded, it's nonlinear, a wind power curve is the same for solar energy. But then what I teach you is linear regression. It's a bit embarrassing, right? So now we have to go to nonlinear. Do you know how to do nonlinear regression? Do you have an idea of, is this easy or not easy? Is this easy? Kind of. Yeah? Do you have an idea? Vasilis? The microphone has disappeared. Yeah, and we shouldn't throw this way. No, there's no laptop on the way. Good. There's his head, yeah.
So basically, we can define different bases for the regression. Right now, we had an affine function, but we can use polynomials or different type of nonlinear functions.
Yes, very good idea. So I have a friend who's been teaching this kind of thing for quite a while. That's one of his main fights, to explain to students that nonlinear regression can actually just be linear regression, but with some kind of nonlinear basis components, right? Here, our component as input is directly x here, right? But we could change that, right? That's what we're going to do now. It could be x squared. It could be some log of x. It could be something else. And if you have some nonlinear function of your input variable as input, you can still have a linear model in terms of the parameters are just let's say, times directly this nonlinear function. So it's still a linear model, but you can capture nonlinear features, you could say, nonlinear characteristic. So let's do that. I issued, it's me generating the data. We have this kind of scatter plot now. That's the relationship between x, so it can still be wind speed, and y is power, say, okay. And then I fit a line. Doesn't look very good. Actually, a lot of people think, it's good enough. That's okay. It's true. I mean, don't love too much because I'm sure you've done that once, or you will do that once in your life. I've done it. I remember telling my PhD supervisor, I think it's good enough. I think it's good enough. If you're just a bit lazy on a Thursday morning.
You just have to compress the y-axis.
Exactly. Yeah, there's tricks. He knows the tricks. Remember his name, you call him, he knows the tricks. All right, so remember how we write the linear regression model. And I told you now we're going to replace this guy by nonlinear functions of the input, but I still keep as a linear model like that in terms of directly we have the parameters times these components, right? So, sorry, that was here. So you see here, for instance, I just take x and I take it at the power p, and you can say, you know, I do it for increasing p. So you can have beta 0 plus the beta 1x plus beta 2x squared plus beta 3x cubed, etc., etc. But you shouldn't go too far with that because it's going to get crazy. But still, in principle, you can go as far as you want, all right? The principle is the same as before. We can write it in a compact manner. We have more beta with proper indices, beta 0, beta 1, etc. And then we have more values in the x input vector. Instead of just 1 and xt, then now we have xt squared, x cubed, etc., etc. Okay? But we can use exactly the same idea as before. Since it's a linear regression model, we only have to change the design matrix. Instead of having only 2 columns, now we're going to have these extra columns with the squared, with the cube, etc. The response vector is the same. We want to estimate more parameters here, but that's why it's reflected by the fact you have more columns here. But it's exactly the same idea, right? So now, since I got the lesson from my PhD supervisor, I look at the scatter plot and I'm like, I think it's quadratic. So I'm going to go to p equal 2, all right? You could try p equals 3, actually. But you would hope that the beta in front of the cubic term is going to be 0. And that's the model telling you shouldn't go cubic, right? So we do that.
But you go for a trial and error. Just you have a look and then you say it's quadratic or cubic.
But so you can go old-fashioned modeler way, do it that way, or you can go modern data science way and do cross-validation and try to see what is best, right? But yes, that's the way. So I do that. You see, I fit a quadratic. I fit a cubic. They look the same. It looks very good, actually. And then if you look at the coefficients, you see the beta I estimated is equal to 0 for any p that is more than 2. So that kind of confirms there is only just a quadratic relationship, okay? So you can do that in a very, very simple way. MATLAB has it directly, by the way, in some function. R also, I'm sure, has a polynomial fit, and Python. The thing is that you can have some very spurious results where you try to increase the order and where you're obsessed with fitting these kind of models to data that are a bit more complicated. So this would be the example for a power curve, for a wind farm power curve. You see, that would be a power curve or generated myself. Okay, it's a bit cheating, but still it's much better if I want to make some illustrative example. So this is the power curve, and I fit a third order polynomial to that. You see, even though in this nice control environment it looked perfect, when you fit a third order polynomial to some actual wind power data, it doesn't look that good anymore, okay? So maybe it's not such a very good idea. Sorry for that. So many people will do it. Sometimes you're lucky and it works quite okay. Most often it doesn't work nicely. So you need to look at something else. Do you have some ideas? Yes?
Logistic function of cosinus?
Okay. That's he said logistic functions or sine, cosine, trigonometric stuff. Yes? Same story. Okay. Yes?
You can define like 3 piecewise functions, with one going through the origin and one through like the rated wind speed, and then.
Yeah. Okay, so we're going to slice the data. That's a good idea. Vasilis, you were going to say that also? Or?
Yeah, and then maybe symbolic regression.
Yeah. So you can. There are many ways to do it. I mean, you're right. You can try more advanced functions, but it gets more and more difficult to fit. you may start slicing the data, or you may start changing your idea of basis functions for the fitting. Okay, good. But so there's really this thing that you could do. It's called local polynomial regression. We use this same test case with data, and instead of saying we're going to fit a model once and for all, we're going to say I want to fit a model in the neighborhood of a certain point. So what would be the model if I was fitting it here, just here, right? And we're going to do it for a lot of fitting points. So at 0, 0.1, 0.2, 0.3, etc. You could have many, okay? For that, I'm going to do weighted least square regression. So that means I'm going to have a weighting function like this. And then when I fit a model, I say that let's say I want to fit the model here. And the importance of the data points I have on both sides is going to decrease with this weighting function. So somehow here you have a window that you only consider the data point in this area, and you give them a weight that decreases with the distance from your fitting point. So the fitting point is at, I cannot see very well here, 0.6 it seems, okay? Oh yeah, it's written. So it's at 0.6. I don't want you to master that right away, but just so that you see the idea, right? So let's do that. We have weighted least square. You just have an extra matrix that comes, which is the matrix of weight that's given by this kernel here, this weighting function. But you can directly use the least square idea also. It's an extension to weighted least square. And we can estimate coefficients for local models at each and every fitting point. So if you were to apply that, for instance, we have this fitting point here. I fit a linear regression model just in the neighborhood. You see, it looks like that. I can do it also with a second order polynomial if I want at another fitting point. It would look like that. And then every time I fit a model, I only keep the value that I fitted at this fitting point. I don't need to care about everything. I just want to keep the value here. You could also keep value in the neighborhood if you wanted. And then I put them all together. All right? Since I locally fitted these models, then I end up with something that's very nice describing the cloud of points. And I never had to make assumption on what's truly the shape of this function. It's just locally linear or locally quadratic, okay? So this is something that is very good. But eventually, you're going to have a lot of meta parameters. Imagine you have to decide where these fitting points are. Is this going to be linear or quadratic? What kernel am I going to use? What are the parameters of my kernels, right? So there's going to be a lot of annoying tuning. Okay, but now we're going to go for the online learning for the last 10, 15 minutes. How many of you have done some online learning? Also none? One person, right? So I'm lucky that you've not done that. It's going to be, so the introduction is quite smooth after what we did. What I would like you to see is that online learning is just a little tweak to whatever we've seen before. And you're going to see the tweak is actually quite straightforward. So why do we want to do online learning? First of all, renewable energy generation is non-stationary. So in energy, when it comes to learning and model fitting, I think all this idea really comes from renewable energy forecasting. People have noticed it's changing with time. We have to be careful with the models that we fit. That can be due to the season, that can be due to the condition of assets, so dirt on blades, whatever. And then we want to have models that change with time. Then another reason why we want to do that, if you do online learning, you're going to do it recursive. You know, you remember what recursive means? First course in computer science? Recursive means that instead of computing based on all data you have, you only update based on the relationship between the last data point and the new data point, right? So it's just single updates all the time, but if you pull the string, somehow you covered all your data sets. But it's very cheap operations to make. And then when you get new data points, you just apply this cheap operation and you update your knowledge, your parameters. So let's look at some example. It is again a nice cloud of points, right? It's very cloudy. What do you say when you see that? Linear, quadratic, cubic? Noisy? Annoying? I'm getting tired. So I would say it's quadratic, but I would say it looks fishy. It also looks fishy because there's a lot of noise. And when there's a lot of noise, you have to wonder, is this signal or is this noise, right? And this signal, let me show you. I generated the data myself, so I know, right? If I slice the data set taking the first 200 data points or the last 200 data points, and I make a scatter plot, this is how they look like, right? So this is actually a combination of different relationships. If you put everything together, it just looks funny and noisy, but actually what's happening is more that it's different things in there, right? When you put that, so it's 1,000 hours, the first 200 hours is like that, I guess the next 200 hours is like that, the following 200 hours is like that, and at the end it's completely different, right? So that's really this motivation for online learning. We want to adapt to the fact that the relationship is going to change with time. How do we do that? Instead of estimating this model parameter at once, remember what I showed you at the beginning, I can have sliding windows. If you always estimate based on the last 200 observation, you should have the most up-to-date knowledge in terms of what's going on, right? We use the same idea as before, and we are at a given time t. We have a window of size n. We collect all this data in the past. We put them into our design matrix and response vector, etc. And see, now it's a 100 window size here, and at each and every time I have this data from the past, I estimate my parameters, I just plot them here, and then I slide my window, okay? You can see that I managed to track the parameters. I really managed to adapt to that. And then if I was to plot the type of relationship, I believe, between x and y we have, this is the relationship I think there is at the beginning. Later it becomes this relationship, and at the end it becomes this relationship, right? So I really adapt to the way the signal in the data is changing. The issue, though, is that it's very heavy. This looks very easy, but there's this one little thing that's annoying. It's inverting a matrix. And if you remember your linear algebra course, inverting a matrix is annoying. It's one of the most annoying operations one can have to do. So we would like to avoid that, because here every time I slide my window, I make a new matrix and I have to invert it. But remember, if I have a window of size 100, I slide it by one time step. How different is that? Only by one element? I mean, so it's a bit ridiculous. It's almost the same matrix, and I still have to invert it from scratch. So I could be a bit smarter about it. And that's why we do this online learning with recursivity. What we're going to do is to say that we add the parameters already for the light time step. So if you estimate it once at first, you have an initial value, or you can start from 0, 0, you know, you don't know whatever. And then every time we're going to have new data, we're going to make an update, okay? And we'll discuss the update in the hands-on session. But the updates would be something like the new value of the parameters is the last value of the parameters plus a function of my new data point and some kind of update rule, okay? You'll see it can be extremely easy. And then it's only based on matrix multiplication. We try to avoid inverting matrices. In the example we'll have in the hands-on, you still have to invert a matrix, but it's timed 2 by 2. So it's almost you could do it by hand, right? Okay, we need an initialization, and we'll discuss that later. The method we'll use, so you already have the solution of the problem 1 in the hands-on, but you don't know how to get it, so that's why we'll work on it. We have this recursive least square. The recursive least square will try to minimize this loss function. It's still a least square loss function, but what we added there here is exponential forgetting. So that's what we heard earlier. You know, we want to weight the observation from the past to give more weight to recent information. And that's very nice when we do recursive estimation, because we'll have this block here. This matrix R is 2 by 2, for instance, if you have only 2 parameters. And this matrix is keeping the information about your input data. So every time you have new input data, xt, you multiply your forgetting factor by the previous information. So let's say it's 0.99. So you do 0.99 times what I already had. So you forget a little bit. And then you put the new information with xt transpose. Then when you updated your information about the input variable, this would be the update rule for your model parameters. The new model parameters is the previous one plus my information matrix that I'll have to invert. As I said, we could avoid it, but for simplicity, we keep this inversion. It's 2 by 2 only. I multiply by my new information, and this is the forecast errors I would have made if using my last parameters, okay? So it's very simple update rule. And if you use that recursively through the data set, This is what it does. It also tracks the change in parameters, and it's so cheap. You just plug it, you let it iterate, it's just so cheap. So this kind of thing, and you see it does the same. This kind of thing, it's something that, I mean, personally, I do systematically. Whenever I do learning, everything has to go online because it's so cheap and it adapts to any changes, right? So that's why I would like you to try it out in the hands-on session. Do you have a question? Yes? You need the microphone? Yeah.
Is the forgetting factor something you set, or is it a hyperparameter of your module?
Yeah, so that's the question that is left. Well done. We again have another meta parameters. And that's why normally we have this next part on cross-validation. The price to pay of all this nice modeling we do, nonlinear regression, online learning, etc., we will always be stuck with some kind of meta parameters. And then we heard, I think a few of you were saying stuff that goes in line with, I mean, we have expert knowledge, you know. So as with your expert knowledge, you could be able to set up these parameters. I've been doing that for so many years. I have an idea of how to set up these meta parameters. But then there's a very data-driven approach, and cross-validation is like the leading approach in machine learning, where you're just going to try different values, and depending on what you get with the different values, you're going to decide on the optimal one, all right? In a very data-driven manner. So I hope he answers your question. Yeah? Yeah. Can you throw the microphone again? Whoa!
Thank you.
That was a revenge you were trying.
How do you manage, like, you have that your regressor is also a time series, and it can be non-stationary.
Yeah.
Sometimes the problem when you do regression on time series is that you have spurious regression.
Yeah, yeah.
Relationships that
Yeah.
seem to be right in the parameters, but they don't exist
Yeah.
in real life. How do you actually manage that?
Okay, I mean, that's a Statistics 101 course that we do today, Statistical Learning 101. So, I mean, there are many approaches to look at that. Some are very easy extension of what I showed here. Some are extremely complex. So a very easy extension would be some robust online learning. And so directly, somehow, as you make your updates, you would look at the new information and you would have some kind of likelihood test that this new information is generating from the process you expect to play with, right? If it's not, you downweight this information, right? So there are ways to, in an online learning environment, to also have some smart view on these two guys, because you have new information and you have the forecast error that's supposed to inform you on how you need to update. And you can put filters on these two guys so that you say, wait, this cannot be right. There has to be something happening, right? After, if you go to the statistical literature and you push even further, there are people, what they do is that instead of having one single model, they have a bank of models, they have a catalog of models. And then when there's something weird happening, they say, maybe my model is wrong now, I need to switch to another model, right? And switch again and switch again. So there are lots of different ideas, but I don't think it's for today. Except if you want to do that, we can upgrade the hands-on and go a bit more complicated. Some other question? Yes?
About the plot of the previous slide, I mean,
this one?
Yeah, you're trying to track the one of the two models you have.
Yeah, I said there is a quadratic regression between Q and Y. So it's it's beta 0 plus beta 1x plus beta 2x squared. But I think the beta coefficient will change with time. So this line is represented by the beta coefficient I get at time t equal 101. This line is at t 500, etc. Okay. The time. Okay. Yeah, the purple might be a bit light to see. Some other question? Yes, there's a question here. Careful.
Could you explain why the dimension of R is only 2 or 3, what as you
Oh,
said?
yeah. Sorry, it's because of the hands-on example. I was just referring to that. The dimension of R...
In the end, it's much lower than the other matrix that we had to invert.
Yes, so you see R is x times x transpose. So the dimension of x is linked to the number of input variables that you have. So if you have an intercept and two input variables, x and x squared, here it's 3 by 3, right? Okay, yeah. So Okay? Some other comments? We'll go through that in the end-on session anyway. Good. Last question. Wait. This is a tricky one. Oh my God, you're good.
You had a graph next to two graphs next to each other. There was a question about the one on the right.
This one?
No, sorry, with the lines that we couldn't see. Yeah, on the left. Okay, sorry, it's a little different than on the slides online.
Really?
Yeah, it's because online it's a little disturbing in the when you're close. There it is. Yeah.
What's disturbing?
Are you worried about the first observations? Because it jumps a little and then it finds a level, kind of.
Oh, here.
The
Okay.
betas.
So that's something we'll do in the end-on. Sorry, I didn't want to discuss it. Sure. So, I mean, there's initialization. It's always an issue. If you do this batch learning, you directly take 100 observation, your first-time window, and you fit a model, okay? But when I do online learning, I start from 0 observation. And when you start learning from 0 observation, you get a first observation, a second observation. If you try to deduce what the parameters value are, you're really in the dark, you know. So you're shooting all over the place. And as you get more and more information, you stabilize. So that's what's happening here, you know. At the beginning, I just shoot. I was like, I have no idea. You said 3, so okay, let's try that. And then eventually you manage to catch up with the line, and then you track it up, right? And your ability also, like the variability you see in this line, would be a function of the forgetting factor that you use. So here I use 0.99. If I was using a higher value, it would be smoother, but maybe I don't track as well the line. If I use a lower value, it's going to be more variable, but maybe I track better the line, okay? So there's this trade-off between tracking ability and smoothness of the trajectory. Okay, should we take a very last question? Then we take 10-minute break. Wow. Guys, it's not good for my heart. I think it's the last time I do this.
It's kind of big question, I think. Like on the first day, we also had this like learning dynamical systems with data. So because your data kind of comes from a physical system, like you have the wind speed and the output, and so you're kind of ignoring this, right? In the whole approach that there's actually physics behind. You're kind of mapping a function. I mean.
Okay. Answer number 1. Who cares? Sorry.
No, but I mean,
but so if you do regression, the way you start with regression, many of the data scientists don't want to know about the physics because they really say it's data-driven, the name of the summer school, right? And the approach of data science is really, I don't want to have, let's say, a priori ideas about what I'm playing with. I really want to be fully data-driven. And I think that's actually a good idea because sometimes if you focus too much on the physics, you're going to put yourself in a corner. You believe only this class of models should be used, the parameters should have this kind of value and so on. So you have too much prior. You know, if you were Bayesian statistics, you have a prior to start with, and you have too much of a strong prior. Well, if you do it fully data-driven, you might be a bit more open-minded. Optimally, what you want to do is to combine the two. So, and that's, for instance, that's what we would do in this case, right? I mean, I know there is a power curve. I know what it is. Even though I say it's going to deviate from the manufacturer power curve, come on, I know it's going to have this nonlinear shape. I know it's going to be bounded, right? So you use this knowledge in your regression framework or any kind of framework you're going to use. So there are people today, for instance, when they do crazy stuff with neural networks, still in the design of the neural networks, they use information about the physics. So if you have some kind of network-based process, you know, for instance, it's going to be extremely sparse, and you're going to have some diffusion from one node to the next following the topology. So your neural network could actually adapt to that. And the way you design your neural network is made for that, right? So there's this kind of things. Again, for a 101 course in learning, I think it's okay not to try to blend the physics with... No, it's a very good question. You're totally right. So, the way I did it is that the slides don't have the solutions, and I will update the slides with the solutions in a few days or a week so that you can still work on it at home if you want, and you'll have the solutions afterward. There are 2 parts, conceptually 2 parts to the hands-on. One is the pen and paper. So it's going back to your linear algebra course and stuff like that. And the second part is implementation. So you use your favorite program, R, MATLAB, or Python. If you don't want to program, you sit next to someone who is going to program for you. That feels good, I can tell you. And then we're going to implement this online learning stuff. Okay? So we're going to stay with fairly simple setups. And if you want to go to more advanced setups, if some of you say, Pierre, it's too easy for me, can we do something more complicated? I can make it more complicated for you if you want. And also, if you like it and you want to push a bit more, you can also write to me and I will give you some more advanced version of that, okay? So, as I said, first part is deriving formulas for online learning in linear regression problems. We're going to keep it linear because eventually I showed you that we can do nonlinear regression with linear regression at the end of the day. We will use it to apply to simple synthetic data sets. And the last data set is actually a real-world data set. It's a portfolio of Australian wind farms where I made a little data set for you. And you can apply that to this Australian data set to fit the model. And then if you want to play a bit more, you can issue forecast also based on this model and see how it goes. All right? Good. So there's two types of models that are nice to consider. And at the end of the day, you see they look the same. When you write them in a compact manner, it's always going to be a beta transpose X, right? Plus some noise. It's just that when you roll it out, it's just a different thing. So the first model is a simple mapping, a simple regression from xt to yt. So that's linear regression. And you could say its wind speed as x and yt is power, for instance. Okay? And you have two coefficients to estimate. The trick is that we have a little t here, so we assume that the coefficients will change with time. Okay? And the second one is an autoregressive model, and that's what I mentioned earlier to someone. So we have a linear regression at the end, but if we roll it out, we say that what we observe at time t is a function of what we observe at previous times. So beta 0 plus beta 1 yt minus 1 plus, okay? But written in a compact manner, it's the same as the other one. If you take only p equal to 1, you have two parameters to estimate, and it's only the way you build your input vector. Instead of being a 1 and xt, it's a 1 and yt minus 1, okay? So it's not crazy different in a way, but when you apply it conceptually, it's quite different. Okay, so I told you online learning is about rethinking the least square and do recursive least square. So that's the objective function that we play with. I've put a little half here because you'll see when you do you calculate some derivative, it's nice, it just disappears. So this is the loss function that we want to minimize, right? And we have this forgetting factor where lambda is less than 1, but it should be very close to 1. So typically you take 0.99, 0.995, okay? And how we get this recursive least square, we use a method from optimization, which is very basic. It's Newton-Raphson, right? If you want to solve an optimization problem, the basic convex optimization course would be that if you want to iteratively find a minimum, you are going to iterate on the point you're on the curve, right? And you're going to have a gradient step. So you see, if you look at a quadratic function like that, for instance, if you want to find the minimum at a given time, you're here, right? You find the gradient. You make a step along the gradient, and if you were to continue like that, you're obviously going to find the minimum. We agree? Okay? And there's a way to do it in a smarter way. We need to normalize that or find the optimal gradient step, right? Because the gradient gives you the direction, but then you want to know how far you need to go along this gradient. And how far you need to go, if you normalize by the Hessian, so this second order derivative, the second order derivative is going to inform about the curvature, right? So if it seems to be steep, you can go down. If it gets like smoother, closer to the point, you go slower, okay? So that's what it does, all right? So now, if we want to derive the update scheme, how are we going to do? What do you think? We're going to do it with pen and paper in 2 minutes. Do you have an idea? Too tricky? So it's not that tricky. We are at t minus 1, and we want to find the parameters at time t. Right? Remember, we are at time t minus 1. We want to update to time t. We need this gradient. We need this Hessian. So the first thing we need to do is that we need to write how my new objective function, not that I get one extra data point, is linked to my previous objective function when I had one less data point. Okay? So you have a little mass to separate that. Then you're going to apply the nabla operator to these guys. And then you're going to calculate the Hessian so that you find out how to update the information on this guy and on this guy. Okay? If we write R the Hessian, we will deduce the relationship between RT and RT minus 1. Okay? And finally, when we've done all that, it will be quite obvious how we can find an update for R, so how we go from RT minus 1 to RT, and for the parameters themselves, so how we go from beta t minus 1 to bt. Okay? And when we've done that, the only thing we have left to do is to discuss how we initialize these guys. Is this clear? Cool. So pen and paper. Do you have paper? Cool. So I would propose we take 10 minutes to do that, right? If you're finished before, you can ask for my opinion. If you're stuck, you can ask for my opinion. And I think we're going to ask Jalal to be a TA for the exercise. No, I will help you if you have a problem, okay? In 10 minutes, what I will do, I will give you the solution right away, and I'll update the slides so that you have it for yourself, okay? So let's do it. No, it's no, sorry. It's yeah, okay. There's a typo. It's st minus 1 of beta hat t minus 1. It's in that sense. Sorry. Thank you very much. Tell me.
The equation, it's not visible from the top one.
No, but I will take it down afterwards. It's just for me. I was preparing my correction.
we're using this update instead of like the system of equations for the dynamic system?
So that's how you get there. What I want is that we find out why we get that, right? Okay. So that's what we're doing now. By doing this derivation, we'll end up to this solution eventually. Okay. I want you to understand why we get there. Okay. Yes, yes. I said quickly when I showed it that it was the solution of our first problem.
Oh, okay.
The typo is that the first line is beta t minus 1.
Okay.
Sorry for that. I really didn't see that one. Ça bosse dur. Je vois. I was telling you it's not mandatory, the update of the abstract.
Yeah.
Because you said you were busy and stuff. I say if you want to improve, there is a...
Next week, during the power tech, I can do it.
Okay. Your poster is good. The main issue I would have is really, I would say, related to presentation. The last box, voilà, you already corrected the bottom box. It was going to the very bottom of the poster. It was weird.
Yeah.
And then in general, it's a bit too heavy and not visually not really optimized. See, this one should be centered somehow, and the color. Oh, sorry, the color of the title.
Yeah.
You already did. You see, you have it in you.
Okay. No, but more
Minimize the text. No, the content is good. Yeah, the content is good. I didn't understand why you wanted to put some text here. You just do it in the most light manner, right?
Okay, I can just say.
But here you write a sentence, an actual sentence.
Okay, so just to compact those, reduce cost of real-time purchase.
Yeah. Yes. So try to compact it as much as possible.
Okay. And do you think, like the conclusions in general, you include them in the poster, or I can just avoid?
Yeah, but it could be key takeaway messages more than conclusions, right?
Yeah.
So it's more if you guys were just taking a picture of a corner of my poster, that would be the corner, and you can bring that home. And that's what I wrote to you also in terms of the PSCC abstract, what to expect, very basic high-level stuff like uniqueness of the equilibria, existence, optimality, how these are affected. For me, these are takeaway messages. And you can have some things that are more applied, like in terms of cost, so suboptimality brought in by bounded rationality, complexity of accounting for it also. Yeah. Is this fundamentally easy or difficult, So these kind of things. Because
so
here,
like key messages.
That's my point. It's too texty, There's too much text, and I don't want to read when I look at a poster. Okay. It's just key messages. No, but it's good. It's very good on there. Yeah. Yes.
Just very simple question. The first one is st beta minus t minus 1.
Yeah.
But what we are trying to write is st, the same thing as the first?
Yeah, but as a function of st minus 1 of beta t minus 1 and some other things.
St minus... yeah, I see. Thank you.
So this one, the first thing we write is st minus 1 or st, because we already have this function.
It's st, you want to rewrite it as a function of st minus 1, okay? So let me... I can give you the trick for the first one, if you want. Don't have enough room. Okay, so if you look at that, the first line, you see this is st of beta t minus 1, right? And I just rewrite it by splitting it. So instead of summing to time t, I'm going to sum to time t minus 1, all right? and I have this extra term then that I'm missing in this sum, okay? But if I do that, here I recognize this is st minus 1. Do we agree? Since now that I wrote my, my sum with that, just I think I'm consistent with my notation up there, so that's good. All right. So actually what we get okay, that's the thing here. We have one thing that we missed is that since we downgraded our lambda, we actually have a lambda that multiply st minus 1 plus this new element, right? Okay. Okay, so we can write st of beta t minus 1 as lambda times st minus 1 of beta t minus 1 plus this new forecast error times 1/2 the forecast error squared. Okay, so if we write it like that, if you want to know the relationship in terms of gradients, you say that the gradient of that is equal to the gradient of that plus the gradient of that. We agree? Okay. So you have to write that down now. And same story with the Hessian. We just have to do one more layer of derivation. Okay? And remember, what you want to do is link now the gradient of st to the gradient of st minus 1. And the Hessian of st with the Hessian of st minus 1. So I mean, let's do it together. Do you have an idea of how it writes? Someone has managed? If you take the gradient of that, what's going to happen? If you take the gradient of this part, you're going to have lambda right, plus, and then you know how to derivate that, right? We derivate, right? And then what's going to happen? You have to multiply by 2 because it's squared, right? You have to take the derivative of this guy, and then what you're going to get is like 2 times 1/2 times minus 1 times, yes, xt times yt minus. Do we agree? Okay. So this guy took. So this is going to be the way we linked our gradients. So the gradient at time t is equal to lambda, the gradient at time t plus t minus 1, minus xt times the forecast error. Yt minus beta t minus 1 hat xt is the forecast error if I use my previous coefficient. Okay? And if we were to do it another time, here, again, we're going to derivate. So we have a minus that comes out, and we already have a minus. And sorry? Yeah, exactly. So, and then what we're going to get is plus xt transpose. Okay? Because you have to think these are vectors and matrices, all right? Are you okay with that? Yes?
Sorry, we can't see. The sunlight is kind of...
Oh! I hesitated in plus taking the middle one. That's a bit silly. Let me try that. So we're going to go in the dark.
Just for a bit.
Just for a quick nap, and then we come back, right? Do you tell me when you can see?
Yeah, still not. It's become really dark. You can see the first line now.
Okay. Sorry, it's too fancy, this thing, like. Okay. Now can you see?
Yeah, that's better. Thanks.
Okay. So now I'm even warmer. I feel even warmer. Okay? So these are the equations we needed to derive. And now if we use these equations, what is going to happen? I'm going to put myself in the middle now. We see that at a given time t, if I'm a given time t, right, I have beta t minus 1 hat, okay? The first thing I'm going to need to do is that I can calculate my forecast error if I was to use my last set of parameters with my new data. So I calculate my forecast error. We're going to call it this. Okay? Then when I have this forecast error, I say, okay, but then I would like to update my information about the processes. And I said here for convenience, because it's a bit heavy, the notation, we're going to call it RT, this information. So we update our information. Okay? And after we've updated this information, we can use the gradient step that I was telling you about. And the gradient step, we were saying that the new value of the parameter is equal to the last value minus the gradient. And the gradient, we know how to have it from here, okay? Divided by the Hn. And the Hn, we have it here, okay? So eventually, what we'll get is, that was in part 2. I have to go back to part 2. Voilà, that's the updates we're having before. If you just do quickly the math, that's going to give that, right? So it's going to be, is this going to be a plus? Yeah, plus. Okay. It's just the notation is different because the epsilon t, I wrote it in full on the slides. But you have it here, I mean, so. Okay. All right. So you see, it's, I mean, you need to know the few tricks on the way on how you split and how you write the math. But eventually, we end up with this two-step update that I showed you earlier. And that means that now we can write, so in Python or in MATLAB or in R, this kind of algorithm where for a given time t, we think we already have beta t minus 1. And we make this kind of updates, okay? So that means you're going to need to track a set of parameters, but you also need to keep in memory this matrix R, okay? And if you have n parameters in your model, the size of this matrix is n by n. So if okay. Now it's a bit stupid because I use R and R, but sorry for that. Okay. Good. Do you have some question? How would you initialize these guys then? Because I say I'm at a given time t, but we have to start from time t equals 0. And the idea of recursivity is that you need to know from t, you know how to go from t minus 1 to t, but you have to decide how you start. What's the first go? How would you start? Someone was ready to try something. There's something, a way to start that's amazing. If I put everything at 0, that means I know nothing about what's going on, right? And I was telling to someone during the break, what you can do also, and that's a question we had earlier, you can use prior knowledge. So if you already had an idea, you had information from the past. So I mean, this is a 0 of size n by n, and this is a 0 of size n. Huh? So if you had already information from the past, you could initialize to some other value. Yes?
Do you have a problem with R0 being 0 for the inverted?
Thank you very much. I will give you the job as TA for next year. So yes. That's the known problem, that when you initialize, and that's why we had this bumpy ride at the beginning we were told about. If you directly try to invert this matrix, and that's what I told you, you're going to have to invert a matrix at each and every time step. It's just exploding, okay? So normally what we do is that we say we're going to pile up some information from time t0, but then we're only going to invert when we feel we have enough information. The way to do that, if you remember again your linear algebra course, you can check the condition number of your matrix, right? So you try to see somehow if your matrix is full rank or not, or what's in there, okay? A more pragmatic way is to say, okay, I'm going to pile up some information in R, and I only apply this update when t is more, let's say, than 20. So you first do only this guy for 20 time step, so that you build up information. Hopefully, if there was information in there, this guy is not singular anymore, and you can invert it, and you can use it for the other step, okay? So that's what we'll do when we implement. Okay. Yes?
If you don't have any a priori, why would you choose more 0 than any other value?
You're totally right. 0 is just the easiest. No, personally, I mean, actually, it depends on the process you care about. But often, for me, it's a 0. Sorry, it's a 0, except for 1. I will have one of the elements I that's going to be equal to 1. Because for many applications, like this autoregressive model, for instance, it makes sense that you say, if I don't know anything else, I say that the value at time t is equal to the value at time t minus 1. So that means that in your regression, beta 1 is equal to 1, right? So there are many applications where your prior is actually that it's not all zeros, but you can have a 1. Or it can be something else. Okay? Good. So let's go for application. We're going to, oops, I erased. Sorry for that. I propose that we use like 15 minutes to try it out now, and then we'll do half an hour more after lunch. We're going to do it for some synthetic data, and we have a linear regression. The thing is that I generated the data myself, so I generated the parameters, I generated the input x, and now you have to figure it out by yourself. Okay? That's what the data look like. So you've seen a few data sets in my lectures before. You have time in the x-axis, right? And at each time, there is a value of x and a value of y. Okay? So here I only show you the value of y, but there's a value of x in the data set. So that's the regression you want to learn is y equal beta 0 plus beta 1 x. But the parameters have to change with time. Okay? So these are, you have the slides normally on your computer. This is an hyperlink, so you can have the data. By clicking on this hyperlink, it's a CSV file, so you should be able to open it with whatever you want to use. Be careful, because in the CSV file, there's a header with the name of the variable, so x and y. If you use R, you may want to keep it. If you use something else, you may want to remove it. But just so that you know, the first one is x, the second one is y. And then I gave you the true parameters, so that when you do the online learning, after you can compare, you know, what you have at each and every time t in terms of parameters and what you get. By default, I would say use lambda equal to 0.99. Okay? So let's try it out. Who doesn't know how to program at all? Ah, you can all program. Cool. So good luck. I can help you. Also, just raise your hand. I'm not very good with MATLAB. I'm losing my MATLAB once in a while. So. Yeah, the link is clickable. See, when I'm here, it becomes a little hand. Yeah, the word link, sorry, it's my way to do things. So if you click on the word link, you have the data that appears here, right? And if you open, you see that's the data. The row line, the row number is the time index. And then on the left, the first column is x, so that's your input. And the right column is y, it's your output. And if you plot you plot y, you will see what I showed you just before here. Okay? So someone was mentioning earlier, what about seasonality? I think here there's clearly some seasonality, and we're going to see if we can track that, okay? So let's try for 15 minutes. So you will see it's actually only a 6 line of code to program that when you know how to do it. It's the first time, so you're going to have to think about it thoroughly, but at the end it's only 6 lines of code. So in our case, the size of beta is 2, and the size of R is 2 by 2, okay? Okay, so that's how to look at these guys. Who is using R? Some people are using R? Oh, you're very few. Okay, okay. So, sorry. Because R is the easiest, sorry to say. Yeah, see, I started and then I stopped. Yeah, I was going a bit quick. Thank you, thank you. Thank you. I stopped putting my transpose, sorry, thanks. Thank you very much. Comment, Carsten.
I just don't get.
Okay, so it's about if you start derivating, if you have only one variable, okay, you see how it works. But when you start playing with vectors and matrices, right? The way you're going to derivate this thing, it has to be a Hessian. It's going to be a 2 by 2 matrix Hessian, right? With the first element, you know, is the first element of this guy derive the derivative with respect to beta 1, and then you have the second element derivative with the other one of xt, right? So here you have two elements in the beta 1, right? So you have to consider the two combination, and that becomes xt transpose because of that, okay? That's just the basic linear algebra. When you're at a given time t, the new information you have, it's a 1. You know, when you want to make your vector xt that you're going to use here for calculating the error, for updating your information, etc., it's 1 and the new value of the vector x that you're observing at time t, right? So it's dimension 2, okay? Just to be sure we agree on that.